Outline 7, Roman numeral number 5, standard enthalpies of formation, delta HF. In the previous two parts, we've covered two ways to determine delta H reaction. One is coffee cup calorimetry, the second is using Hess's law, and the third way is to use standard enthalpies of formation, delta HF. Before I tell you how to find delta H reaction, I just want to tell you what delta HFs are. They are delta H of formations. Delta H formation. And all values of delta H reaction are relative. There are no absolute values of delta H reaction. We've talked about previously how delta H reaction is related to the change in potential energy of the reactant bonds becoming product bonds. And since they're potential energies, they are energies of position. And if we were to think about a ball above the ground, we've previously said that the potential energy is equal to mass times gravity times height, and where height is this distance. And potential energy of this ball is really the change in potential energy as the ball goes from a specific height to the height we're calling zero. There is no such thing as zero height, meaning that height is relative, and therefore the potential energy of this ball is relative. Well, I don't know if that's a justification or a complete justification for the idea that there are no absolute values of delta H reaction. However, that's what we're going to use. So what we do, like when we have a ball above a floor and we call this height equal to a distance of 0, then we can measure things relative to that. We will also define a 0 for delta H, and each element gets its own 0. Chemists and scientists in general have found that that's the easiest way to do it. And the most convenient reference point for each element is the lowest energy form of each element at 25 degrees Celsius, 1 atmosphere for gases, 1 molarity for aqueous species, and reference state of pure liquids and solids. What does that mean for us? Well, it means that the delta H of formation for oxygen gas, chlorine gas, bromine liquid, all equals 0. And that's by definition, meaning they don't have 0 potential energy, but we are using that as the floor or the 0 point for each of these elements. We could say the same thing for Na solid, zinc solid. Most elements are solids on the periodic table, so most of them go like that. All right. Then for solids, gases, and then when we have compounds, we will measure, or we will tabulate in this case, and what I've got is a table of delta HF values that you will be given on your exams. And what we're going to do is we're going to do what's called a delta HF, or change in enthalpy of formation reaction for sodium chloride solid. And a delta HF reaction for any material has that material as a product. With a 1 coefficient, because we are forming 1 mole of it. It also has reactants as the elements in their lowest energy state. Reactants in their lowest energy state with whatever coefficients they need to balance the equation. All right, so for sodium chloride, that means write sodium chloride as a product. Then think about what the lowest energy states are for each of the elements in sodium chloride. That would be sodium solid. That would be chlorine gas. And I can see that I've got 2 chlorines here, but only 1 chlorine on the product side. I know it's a little weird, but this final answer has a half coefficient in it. And the way that a thermochemist or a thermodynamicist, a scientist who works with thermodynamics and thermochemistry, would look at this is they would say, well, you can't have half a molecule of Cl2, but you can have half a mole. And since most of thermochemistry and thermodynamics was completed before we really knew about atoms and molecules, everybody seems to be fine with that. So from now on, it is okay to have a half coefficient in a balanced reaction if you mean half a mole. That's okay. All right, let's see. So that's a delta HF reaction. The delta HF value, those are what are tabulated over here. We can see, let's see, H2 is 0, O2 is 0. Let's see if we can find Cl2 on here. Cl2 is 0, sodium solid is 0 as well, and sodium chloride solid minus 411.2. And the units of all those on that table are kilojoules per mole. What this reaction says, and this is a delta HF reaction for sodium chloride, is that if we started with sodium solid and half a mole of chlorine gas and made sodium chloride out of them, that process, that reaction would release 411.2 kilojoules per mole. And what the power of delta HF reactions is we'll tabulate all these values and then use them to calculate delta H reaction. So delta H reactions can be determined from delta HF formation values. This is the third way to determine delta H reaction. We have that table of values that I showed you, and the general formula is that delta H reaction equals the sum, this is the Greek uppercase letter sigma, which means sum of coefficients times the delta H reaction of the products, minus the sum of the coefficients times the delta H reaction of the reactants. That's the general formula. Let me show you the applications of it for photosynthesis. Photosynthesis, the question we're going to ask, is it exothermic or endothermic photosynthesis? So in order to do this, what I like to do is go to the table, look up all the delta HF reactions for all of them. If we do, this is going to be minus 393.5, and I'm not doing the coefficient parts yet, I'm just writing the numbers. For H2O liquid there, that's an L, H2O liquid minus 285.8. Aqueous C6H12O6 minus 1263. And oxygen, simply 0. You can look it up or you can know that is the lowest energy state. Now, application of this formula is another application of final state minus initial state. Products will be our final state. So it's going to be delta H reaction products times their coefficient, so 1. And I'm going to omit units here until the end. Plus 6 times 0 minus, and this time it's going to be minus the quantity for all the reactants. So 6 times negative 393.5, that's for my carbon dioxide. Times 6, plus 6 times the value for my H2O, my water. These are going to be double negatives, so these will end up being positive terms. And when we calculate this out, so 1263 minus, I'm just going to do plus, plus, plus. So all of these are positive now. So plus 6 times 393.5 plus 6 times 285.8, and I get 2,812.8 kilojoules per mole. That's positive. This is an endothermic reaction. Takes a lot of energy to do photosynthesis. Where does that energy come from? That's a rhetorical question. It comes from the sun. All right, here, this first one will be a companion problem. It is a combustion reaction. Combustion reactions tend to be exothermic because they are used to create energy. CH4 is methane, also known as natural gas. So when you do this calculation, delta H reaction better be negative, and pretty negative as well. Let's do this one here. It's another combustion reaction, this time for acetylene, C2H2. Let's go to my list, C2H2. Looking up delta H formation values in kilojoules per mole. I have 226.7. Oxygen's just 0. Carbon dioxide. And liquid water here. Good. This time, so products minus reactants using coefficients. That looks about right. This is a positive number, so this will be a negative and subtract it off. Multiply it out. I get 2,599. Kilojoules per mole. Everything's in kilojoules per mole here. That is my change in change in enthalpy of reaction for this process. Now, let's see if I can leave that up there. There we go. Now we're going to do what's called a reaction energy diagram. A reaction energy diagram using the last example. Delta H reaction equals minus 2599 kilojoules per mole. This is a highly exothermic reaction. That means energy is given off. Energy is a product. That's also for an exothermic reaction, another way of looking at it. And an reaction energy diagram, let's see, there we go. There's a reaction. A reaction energy diagram is going to have potential energy on the y-axis. It's going to have something called reaction progress on the x-axis. And for an exothermic reaction, what I'm suggesting is that as you go from reactants to products, our reactants here, 2 C2H2 plus 5 oxygen. As you go from the potential energy stored in the bonds here to the potential energy stored in the bonds of the products, the difference in the potential energy is going to be equal to delta H reaction. Minus 2,599 kilojoules per mole. What this picture does, it's a reaction energy diagram, it nicely illustrates, at least to me, that the potential energy of the reactants in an exothermic reaction is higher than the potential energy of the products. This energy is released to the surroundings. So potential energy released to surroundings as heat that warms the surroundings, raises their temperature and increases their kinetic energy. And so what we have here is a very nice example of potential energy stored in bonds, released as we go from reactants to products to raise temperature and increase the kinetic energy of the surroundings. That's how reactions work, to release energy and create heat for so many processes. Okay, so then we get to the question, why does a chemical reaction tend to occur? Piggybacking off of what we just said and relating it to physics in the same way that a ball will roll down a hill to lower its potential energy. Spontaneously, products will lower their potential, reactants will lower their potential energy to become products in a spontaneous process. And I will be careful here. This is only part of the story. This is Chem 1010. This is only part of the story. So what we will say is that why does a chemical reaction tend to occur? A chemical reaction tends to occur because reactants lower their potential energy as they become products. And in direct analogy to why a ball rolls down a hill. And so we will find that most reactions in Chem 1010 lower the energy of the reactants. and that these are the reactions that tend to occur. We did see a reaction that was endothermic that occurred. I do want to give you the idea that it is a little more complicated, but overall, the vast majority of reactions that occur are exothermic.